Okay, welcome back. So, you may have come up with a certain kind of definition of a projectile. From a physics point of view, it's any object upon which the only force acting is gravity. Now, this is an interesting designation. What does this mean? This means that an object will need to be heavier than air, since buoyancy would be a force acting on this object. And it needs to be moving relatively slow so that drag won't be an issue as well from air. But otherwise, essentially anything on Earth can be a projectile. Um, I guess another thing worth noting is that anything sitting on a table has gravity acting on it, but the table would be pushing upward with a force equal to gravity. And so it's not a projectile for that reason. Now, one thing that you may have defined as a projectile, a rocket, actually isn't, as long as the engine is firing, because that engine is exerting a force to push the rocket forward. Similarly, a plane with a propeller pushing it forward isn't a projectile. But maybe you can come up with some other examples. We can come up with some other examples as well. It amounts to anything, though, that is thrown or dropped. So javelins, arrows, these kinds of things. Anything like that, a ball, a shot put, is an example of a projectile. It is useful to note that projectile does not imply thrown. It could simply be dropped. So a teacup dropping off a table is another example of a projectile. Now here comes the toughest part of this session. Can we think about our knowledge of kinematics and attempt to describe the x and y components of projectile motion individually? And it would be interesting to stop and debate this. It's difficult to do in video form. But what I'd encourage you to do is think about the y motion. Think about the motion of a projectile if we only consider what's happening up and down and what that should look like. So what should if we consider only how a thrown shot put moves down and up, what should be the parameters under which that movement occurs? And similarly, if we only consider how it moves forward, what does that look like? And that's really what we're going to do right here. So first off, if we're considering an object, a projectile, its acceleration will always be downward. And it'll be, of course, 9.8 straight down, regardless of the direction of the projectile's motion. So this is a pretty good diagram right here showing in green the force of gravity acting down and the acceleration due to gravity. The projectile at first is moving up and accelerating down, then moving down and accelerating down. And as we discussed previously, all objects accelerate at 9.8 meters per second squared down. One of the key terms that we use when we talk about projectiles is their trajectory. And this, in gravity, a projectile will always form a kind of a parabola. So here's an example here of a cannon firing directly off of a cliff. And we can see up top the direction of the projectile were there no gravity acting on it. And then the parabola below where the projectile moves downward due to acceleration due to gravity. this picture is perhaps a little more interesting. So if we consider the movement, the gravity-free path, this is really the velocity in the x direction, right? And the vertical motion only, this is our y component of the motion. Now what's interesting here is these may look familiar. We can think of this as time as stop camera photography, so we can see this x component of the motion might look familiar to you from our ticker tape experiment on constant speed. Similarly, our vertical motion might look familiar to you as our acceleration due to gravity lab. And of course, we can add those two things together, and the x and the y motion added together gives us our characteristic parabola projectile motion. If we want to consider the y component of the motion, essentially all of our uniform acceleration equations apply to that y case. One of the more useful cases is this one, where we have our displacement in the y direction given by the initial y velocity times the duration of the experiment plus 1/2 of the acceleration times duration squared. And of course the acceleration is negative g, or negative 9.8 meters per second squared. And we can say that while the horizontal component remains constant motion, constant velocity, the negative component for our cannonball becomes more and more negative with time. It accelerates downward. And this applies equally if we had fired our cannon up into the air. We have the acceleration down, where it accelerates and begins to move downward faster and faster once it's gotten rid of its upward momentum. Now, another important parameter of a parabola's or a projectile's path is the range. And the range is defined as the horizontal displacement of the projectile. And it's given by a very simple equation that we've seen many times before. Since there's no acceleration in the horizontal direction, the range is just the velocity in the x direction times the duration of the experiment. That's worth examining again. We have a very, very simple way to describe the movement in the x direction. Now, the duration of the experiment actually has its own term. It's called the hang time, the amount of time the projectile is in the air. And we can say that if we're firing something into the air, the higher the initial vertical velocity, the longer the hang time will be. Or we can say the higher up it is, if we're dropping it, the longer its hang time. Now, in this case, we drop this ball from a high height versus throwing it upward. One is in the air twice as long as the other, so we say its hang time is twice as much. Now, something worth noting is that for those two equations, the x and the y case, the only shared term is that hang time. That's the duration of the experiment. And that hang time is a critical parameter in defining the movement of projectiles. Often, it's our challenge to find out the hang time and then to use that with the horizontal speed to get the range. Okay, now we'll move to the cannon simulator activity. We can use this to practice getting x and y components of the initial velocity, and we can look at the effects of things like angle on the range of a given projectile. So I'd invite you to go and open up that activity and get to work. Thank you for your time.